finally, it is concept map time. So we have a whole bunch of physical constants that we've defined, and I'm going to try to use as much space here as I can. So we first started with this thing called charge, and then we said, well, when charges flow, that means that there's a current, and charges they create an electric field. And there's when we have an electric field and we integrate that over an area, there's a flux, and that's the electric flux that is associated. So those are the concepts that we needed. And then, of course, there was the Coulomb force, F sub C. So I'm going to actually write this out. So then we started talking about circuits, and we said, well, there's this thing that is an associated physical quantity called potential. And then when we were doing circuits, we also needed we needed to define the resistance, and we needed to define the electromotive force, or in other words, batteries. And that was the end of circuits. Now then we jumped into magnetism, and we said, well, there's this object called a magnetic field, and when the magnetic field is when a charge is moving through the field, there's a Coulomb force, Lorentz force, and that's let me draw that here, F Lorentz. There's a Lorentz force that is felt, and then there was also a flux for magnetic fields, and these are the basic physical constants that we introduced. Okay, now I'm going to take a picture of this, and I want you to start connecting and annotating the relations, and maybe it's an arrow, maybe it's a circle, the relations between all these objects, and make sure that we know what they, make sure that I see that you know what the relation is. So these diagrams, whenever I make them, they always look different, and they always end up being quite messy, and it's usually not the final product that helps you organize these things in your head. It's usually the process of putting it together. So we started with this thing called charge, and when it flows, it's a current, right? So there's a back and forth. There's a I is dq dt, and reverse is the integral. Then in vacuum, this charge generates an electric field. So there's a dE is kq r at r squared, okay, over r squared. And then with an electric field, there's an associated quantity. That's the integral of EdA. I'm going to drop all the vector signs, okay, because otherwise it gets a little messy. And then we said that there's this one very specific case where if you have a flux that goes through a Gaussian surface, that the flux is equal to Q over epsilon naught, and that's Maxwell 1 or Gauss's law. So put these together. Okay, so that's Maxwell 1, phi E is Q epsilon naught. Okay, so that allows you to go from Q to E through the flux without having to do direct integration. All right, so that was our first one, and then we said, well, there's a associated quantity that is, delta V is minus EDL. And you can go back and forth. You can take the integral. You can also take the partial derivative if you're going in the opposite direction. And then there was a with this potential, there was a for closed paths, there was law that was Maxwell 2. EDL is 0. And then we started doing circuits, and then we needed a couple of things extra. We needed a V is IR, except it's a little problematic to use the same V because it's not really the same V, but it's still useful to kind of keep them together this way. So to know that, you know, something in volts could look like volts. Okay, so this relation, tying this current and voltage together, the ratio defines this object called a resistance. So then we'll write that here. So that's R is V over I. And then when we started doing more interesting circuits with that, we also needed this object called E. Now, E looks like a voltage, but it has the opposite effect. This is because it can drive a current, and in this case, it's the voltage difference that is dropped due to a resistor. So I'm going to pull these together, and I'm going to say this together is Kirchhoff's voltage law that says that voltages in a closed path are adding up to 0. And then in order to do more advanced circuits, we also needed to use a current law. And for that, we really only needed one effect. And that was the fact that charge is a conserved quantity, or put it another way, I'll put that here because you can say it. Q is conserved, or I in is I out. It relates to both. Okay, so that was the electric sector of Maxwell's equations. Oh, I'm sorry. And of course, once you have the, can't believe I forgot this. Another force, and then that is F is QE. And that relates this Q, that E with another Q. And that's why I'm drawing this thing, because it's not the same Q. All right. Now, Lorentz forces. Lorentz forces were the result of either a magnetic field acting on a current carrying wire or a moving charge. So that was the Lorentz force. Well, I'm going to need another color. And I warned you, this gets messy. Okay, so the Lorentz force here, it says IL cross B or QV cross B. Then with the magnetic field, there's an associated quantity that is phi B is BdA, as always. And then there's a special case, which is Maxwell 3. BdA is 0 for closed Gaussian surfaces. All right. And now the final thing we did today is we added the Biot Savart. So Biot Savart says that if you have some kind of a current, it's going to generate a magnetic field. So that is, oops, that is the other way. So that's this one, and therefore Biot Savart says dB is mu naught IDL cross R 4 pi R squared. All right. And that's the, I would say, the sum total. I mean, there's derived stuff here. There are ancillary laws. For instance, I didn't really specify what K was. And of course, did not specify what mu naught was. Obviously, they're important because they're the thing that does the unit conversions as well as the gives it the physical magnitude. And mu naught and epsilon naught are actually related to each other through a very, very cool law, and we will get to that in a little bit.